Part 1. Rotation. Animating objects is nothing more than rotating them to the correct orientation and then displacing them to the correct position. In this section, we will focus on the rotation part. Chapter A. Vectors. Okay, let's start by defining a vector. So what is a vector? Well, a vector is something with magnitude and direction. It doesn't matter how you do it. All that matters is that you have a direction and you have a magnitude. This could be a vector. Now you could specify the direction by some angle theta, and the magnitude is just the length of that arrow. Now that method of specifying a vector may have its own applications, but we will use another way. Take these 2 points in the Cartesian coordinate system. Call one the tail and the other the head. These 2 points are enough to describe a vector because you can calculate its magnitude and its orientation using trigonometry. Even better than using 2 points, if we move the vector's tail to the origin, we can represent the magnitude and direction with just 1 point. Moving vectors around like this does not change its direction. The angle theta is unchanged. And it does not change its magnitude. Therefore, the vector is unchanged and we can move it like so. Okay, let's do some vector arithmetic. Multiplication with a scalar. Multiplication of a scalar, a single number, just means that you multiply that number to every dimension in the vector. When you multiply a scalar to a vector, you don't change its direction, but you do change its magnitude. Essentially, when you multiply a vector by a number, you are multiplying the magnitude of the vector by that same number. So if you want the magnitude to be halved, multiply by 0.5. If you want the magnitude to be doubled, multiply by 2. Okay, I lied just now. You can change the orientation when you multiply by a scalar, but you can only flip the direction like so. If you want to flip the direction but not change the magnitude, multiply by -1. Vector addition. Adding one vector to another means you just add their respective xy dimensions. We can visualize vector addition by connecting the tail of one vector to the head of the other. Remember, we can do this because, as I mentioned before, it doesn't affect the vector when you displace it like so. By this diagram, we can see the vector that results when we add vector A to vector B. Subtraction. Vector subtraction is like vector addition, except we just subtract the dimensions. To visualize this, we can take cues from our understanding of ordinary addition and multiplication. We can convert numeric subtraction, A minus B, in terms of an addition and a multiplication as A plus minus 1 times B. We could do likewise for vectors. Vector A minus vector B is equal to vector A plus -1 times vector B. We know that multiplying by -1 simply flips the vector, and adding vectors simply puts them in a head-to-tail configuration. Therefore, vector A minus vector B looks like this. So we've seen vectors in 2D, but what about 3D? It's not much different. In multiplication, you multiply the scalar to the third dimension as well. In vector addition and subtraction, you just add or subtract that third dimension. You can still use the same head-to-tail visualization, and multiplying by -1 will flip the vector over all 3 axes. Cross product. The actual math of a cross product is not something you really want to know, at least for this course. Matlab has a built-in cross product function. However, you do need to know what a cross product is trying to do. For our purposes, a cross product is asking the question, if we had vector A and vector B, what is the direction of the vector that is 90 degrees to both vectors? So if we have vector A and vector B, the vector that is 90 degrees is vector C. Now you may be thinking, there are two vectors that can be 90 degrees to vector A and vector B. This one and its opposite. And you'd be right. That's why we have the right-hand rule. The right-hand rule specifies the direction of the resultant vector C. Using your right hand, put your index finger along the same direction as vector A, your middle finger along vector B, and the result, A cross B, will follow your thumb. If it's not working, make sure, as I forgot to do during many physics exams, that you are in fact using your right hand. The right-hand rule determines which of the possible two vectors is the result. As you can see by the right-hand rule, A cross B is different than B cross A, and they differ by one vector being a flipped version of the other. So when you're coding, you really have to be careful of the order. We'll see this in future lessons. Also note, we made no mention to the magnitude of the vector that results from A cross B. This is because for the entire course, we're not going to even care about the magnitude of that vector. We only care about its direction. And we force the magnitude to be equal to 1. This is what we call a unit vector, and you'll see this in future chapters. Making a unit vector. A unit vector is a vector with a magnitude of 1. In this course, we may need to convert some vectors to its unit vector, which means a vector of the same direction, but magnitude 1. To do this, you just need to calculate the magnitude of that vector and divide each dimension by that magnitude. Now, if you want to go into the actual math, it's not hard to find videos to show you how it works, but I'll just provide you with the code to do this. If you input a matrix of vectors, where the columns represent dimensions x, y, z respectively, and the rows delineate each vector, the result will be vectors of the same direction as before, but the magnitude is 1. Organization of vectors in Matlab. When I first started to code for 3D analysis at McGill, I had a choice. Should I arrange my vectors as columns or as rows? It was completely arbitrary. I finally chose to organize vectors as rows because when I viewed hundreds of them in the command window, Matlab lists them vertically and is easier to read. All this to say is that there was no critical reason to organize vectors in this way, and the math is not different. It was just a random decision. That being said, if you do decide to organize your vectors into columns, you're going to have to constantly convert your code, and it's just more trouble than it's worth.